Jupiter's role in our solar system goes far beyond simply being the largest planet orbiting the Sun. Its immense gravitational influence shapes the behavior of countless other objects within the solar system, from asteroids and comets to the very structure of planetary orbits. To understand what Earth might look like without Jupiter, it's essential to appreciate just how pivotal this gas giant is. One of Jupiter's most critical functions is acting as a kind of cosmic shield for Earth. With a mass more than twice that of all the other planets combined, Jupiter's gravitational pull is extraordinarily powerful. This giant planet exerts a strong influence on the population of small bodies, asteroids and comets, that could otherwise pose threats to Earth. Within the asteroid belt, a region between Mars and Jupiter filled with rocky debris left over from the early solar system, Jupiter's gravity continually tugs on these objects. This can result in some asteroids being nudged onto trajectories that cause them to either fall into the Sun or be flung out of the solar system altogether, reducing the chance of those asteroids heading toward the inner planets. Moreover, Jupiter's presence helps to regulate the paths of comets coming from the outer reaches of the solar system. Long-period comets originating from the distant Oort cloud can have highly elongated orbits that bring them close to the Sun. Jupiter's gravity can capture or redirect some of these comets, preventing many from reaching the inner solar system where Earth resides. Without Jupiter's massive gravitational pull, there could be significantly more cometary material reaching Earth's vicinity, potentially increasing the frequency of impacts. Historical records and geological evidence suggest that asteroid and comet impacts have played an influential role in Earth's history, from delivering water and organic molecules that may have contributed to the origins of life to causing mass extinctions that reset the course of evolution. The presence of Jupiter has helped moderate the impact rate, reducing the number of catastrophic collisions and creating a more stable environment for life to develop. Interestingly, Jupiter's protective role does not mean it completely prevents impacts. The Chelyabinsk meteor that exploded over Russia in 2013 and the historic asteroid impact that contributed to the extinction of the dinosaurs 66 million years ago occurred even with Jupiter in the solar system. However, without Jupiter's gravitational influence, these events might be far more common, possibly making the planet far less hospitable for complex life. Beyond protecting Earth, Jupiter also affects how the planets themselves formed and evolved. Early in the solar system's history, the gravity of Jupiter shaped the distribution and movement of the primordial gas and dust cloud from which the planets formed. Jupiter's presence likely prevented the formation of a planet in the area of the asteroid belt by stirring up material and causing microscopic dust and larger rocks to collide at higher speeds, breaking apart rather than sticking together. This phenomenon ensured that the solar system had distinct inner terrestrial planets like Earth and Mars, and outer giant planets like Jupiter and Saturn, rather than a more chaotic mix or additional Earth-like worlds where the asteroid belt lies. In addition, the giant planets' gravity stabilized the orbits of the inner planets, including Earth. Without Jupiter, the gravitational pulls among the remaining planets might have led to more chaotic and less stable orbits, potentially causing larger variations in climate and environmental conditions. Over millions of years, such instabilities might have made it more difficult for life to develop and persist on Earth. Jupiter also influences the structure and behavior of Saturn's rings and moons, as well as its own extensive system of satellites. Its strong gravity creates regions called Lagrange points, where smaller objects can remain in stable positions relative to Jupiter and the Sun. These points host populations of so-called Trojan asteroids that share Jupiter's orbit, held in place by the delicate balance of gravitational forces. Studying these Trojans provides scientists with valuable information about the early solar system and the processes behind planet formation. Without Jupiter, the population of these asteroids and other small bodies in the solar system would be distributed differently, and scientists would have fewer clues to decode the history of our celestial neighborhood. The gas giant acts like a time capsule, preserving material from the dawn of the solar system that can help researchers piece together the origins and evolution of planets, moons, and smaller bodies. Aside from its gravitational influence, Jupiter's strong magnetic field warrants attention. This magnetic field is the largest of any planet in our solar system, generated by the rapid movement of metallic hydrogen inside its interior. Jupiter's magnetosphere extends millions of kilometers into space, shaping the space environment around it and even affecting the solar wind, a stream of charged particles emitted by the sun. While this magnetic shield doesn't directly protect Earth from space weather, it helps control the behavior of charged particles in regions farther from the sun. Jupiter's intense radiation belts, a consequence of its magnetic field trapping charged particles, pose a challenging environment for spacecraft and any hypothetical future human explorers of its moons. However, these belts also offer scientists a natural laboratory for studying space phenomena related to magnetic fields and charged particles, which can improve our understanding of similar processes closer to Earth. The planet's influence even extends to Earth's climate over long periods. Some researchers have suggested that Jupiter's gravitational interactions may contribute to the stability of Earth's orbit and axial tilt, which in turn regulates seasonal patterns and climate. While these effects are subtle and occur over millions of years, the relative steadiness they bring might have been crucial in allowing life to adapt and thrive under consistent environmental conditions. In the absence of Jupiter, Earth could experience more orbital variations, leading to more extreme shifts in climate and possibly destabilizing ecosystems. A scenario hypothesized to make the emergence of complex life more difficult. It's important to recognize that these are ongoing areas of research, but the consensus is clear that Jupiter's presence has helped create a more stable and life-supporting solar system environment. Finally, Jupiter has become a key focus for missions aimed at uncovering the mysteries of our solar system. Space probes like Pioneer, Voyager, Galileo, and the more recent Juno mission have provided unprecedented insight into Jupiter's atmosphere, structure, magnetic field, and moons. These missions have expanded our understanding of giant planets and revealed fascinating features such as Jupiter's Great Red Spot, a massive storm persisting for centuries, and the potential subsurface oceans on its icy moons like Europa, which could harbor conditions suitable for life. Without Jupiter, the narrative arc of space exploration would be quite different, lacking one of the most compelling and instructive bodies in the solar system. The gas giant acts as both protector and storyteller, offering scientists clues to how planetary systems develop and how life-supporting conditions can arise. In summary, Jupiter shapes our solar system in numerous intertwined ways. Acting as a gravitational guardian, it decreases the frequency of potentially devastating impacts on Earth by deflecting or capturing asteroids and comets. It has guided the formation and stability of planets and smaller bodies, maintaining an orderly system that allowed Earth to become a stable home for life. Its massive presence influences not only the paths of celestial objects, but also the conditions on Earth itself. Without Jupiter, the solar system would be a very different and much more hostile place, and the planet we call home might have had a markedly more dangerous and uncertain history. Understanding Jupiter's profound role paints a clearer picture of the delicate balances that make Earth, and life as we know it, possible. Another important aspect to consider when imagining a solar system without Jupiter involves the fate of the other giant planets, particularly Saturn, Uranus, and Neptune. The dynamic interactions among these large worlds have played a critical role in shaping the architecture of our solar system. Jupiter's enormous mass influences the orbits and migrations of its fellow giants, and without its gravitational dominance, the outer solar system might look quite different. In the early days of our cosmic neighborhood, the giant planets did not form where they currently orbit. Instead, evidence suggests they migrated from their original positions in a process linked to the movements of the leftover gas and debris in what was once a protoplanetary disk, the dense disk of gas and dust surrounding the young sun. Jupiter's migration inward and then back outward, a hypothesis supported by models like the Grand Tack, would have altered the distribution of materials across the system. This movement likely influenced the timing of formation and the eventual placement of Saturn, Uranus, and Neptune. Without Jupiter's gravitational push and pull, it's plausible that Saturn and the ice giants would not have followed the paths they did, potentially leading to a less stable arrangement. This could result in more erratic orbits or even collisions between planets or with other debris. The gravitational resonance between Jupiter and Saturn, the way their orbital periods lock into a specific relationship, helps stabilize the solar system over long timescales. The absence of Jupiter means losing this stabilizing influence, which may have led to more chaotic orbital dynamics, impacting the stability of the inner solar system as well. Looking further into the solar system's outermost regions, Jupiter affects the scattered disk and the Oort cloud, two largely unseen but enormous reservoirs of icy bodies. The scattered disk is home to objects with highly eccentric orbits that are shaped by interactions with the giant planets, especially Neptune and Jupiter. The Oort cloud, a theoretical shell of comets surrounding the solar system at immense distances, acts as a source of long-period comets that occasionally visit the inner solar system. Jupiter's powerful gravitational field influences the comets' journeys from these distant zones, either injecting them into the inner solar system or flinging them far away, maintaining a certain balance. Without Jupiter's sorting effect, the flux of comets into the vicinity of the Sun, and by extension, Earth, would likely increase, raising the risk of frequent impacts. This matters not only because of the potential for destruction, but also because impacts have historically contributed to the delivery of essential compounds, such as water and organic molecules. Jupiter's control helps moderate these deliveries, which may have been instrumental in both the development and the ongoing maintenance of life, by regulating the frequency and intensity of comet impacts. Turning our gaze inward again, Jupiter's influence on the inner solar system involves more than just shielding Earth from impacts and stabilizing orbits. Jupiter may also have played a role in shaping the conditions that allowed water to accumulate on Earth, forming oceans crucial for life. Early on, volatile-rich objects like comets and certain asteroids likely delivered significant amounts of water and other key ingredients for habitability. Jupiter's gravitational field guided many of these bodies inward, selectively drawing in some while deflecting others. Without Jupiter, this delicate balance could have tipped in either direction. It's possible that Earth might have received less water, leaving it dry and inhospitable, or conversely, it might have been bombarded with excessively frequent impacts, preventing stable oceans and a nurturing climate from forming. Either scenario would significantly affect Earth's capacity to support life over geological timescales. Furthermore, Jupiter's presence impacts the distribution of the asteroid belt beyond acting as a shield. It shapes the belt's structure by creating gaps known as Kirkwood gaps, regions devoid of asteroids caused by gravitational resonances with Jupiter. These gaps influence how material moves within the belt, potentially affecting how asteroids collide and fragment. Without Jupiter's gravitational hand sculpting the belt, the distribution and migration of these objects could be substantially different. A more homogeneous belt might have led to either more frequent delivery of asteroids to Earth or the formation of a larger planetary body in that region, altering the balance of worlds orbiting the Sun. Considering Jupiter's massive gravitational influence and its associated satellites, the giant planet also impacts the inner solar system in ways that may appear subtle, but are significant over long periods. For example, the planet's pull influences the orbits of Mars and Earth, contributing to the current arrangement that provides Earth with relatively stable climate patterns. Mars, a planet with seasons and polar ice caps, may owe some of its orbital characteristics to Jupiter's tug. Without Jupiter, Mars's orbit might be more eccentric or less favorable to retaining an atmosphere, which could influence its potential as a future habitat or a source of scientific insights regarding planetary habitability. Jupiter also plays a role in the dynamics of near-Earth objects, NEOs, a group of asteroids and comets whose orbits bring them close to our planet. While some NEOs are deflected away by Jupiter, others are placed on paths intersecting Earth's orbit due to the giant's gravitational nudges. The balance between these effects is complex but critical. In a solar system without Jupiter, models suggest the population and behavior of NEOs would differ, potentially increasing the unpredictability of impacts, again raising questions about Earth's suitability for life. Expanding on Jupiter's influence on space exploration, the planet has become a cornerstone for understanding not only giant planets, but also the potential for life elsewhere. Moons like Europa, Ganymede, and Callisto have captivated astronomers and astrobiologists due to the presence of subsurface oceans beneath their icy crusts. These hidden oceans could be among the best candidates for extraterrestrial life within our solar system. Juno, NASA's current mission orbiting Jupiter, continues to probe the planet's atmosphere, gravitational field, and magnetosphere, shedding light on its formation and evolution. This information not only informs us about Jupiter, but also about the processes underpinning planet formation in the broader universe. Without Jupiter, humanity's window into these processes and potential habitats would be much narrower. The absence of such a massive, complex planet would deprive astronomers and planetary scientists of an essential reference point. Many theories about planetary physics, atmospheric dynamics, and magnetospheres are tested and refined based on what we learn from Jupiter. Jupiter's role in generating intense radiation belts, though hazardous for spacecraft, also provides a unique environment for scientific discovery. These belts accelerate and trap charged particles, creating a natural particle accelerator that helps scientists study space weather and magnetic field interactions on a scale difficult to replicate elsewhere. These insights have practical applications, influencing the design of spacecraft and satellites, including those orbiting Earth. In terms of planetary magnetospheres, Jupiter's is a prime example of how magnetic fields interact with stellar wind, the stream of charged particles emitted by the Sun. Studying Jupiter improves our understanding of similar phenomena closer to home and across the galaxy. Without Jupiter's strong magnetic environment to study, advances in space physics would likely be less rapid or comprehensive. Shifting the focus to the long-term future of the solar system, Jupiter's gravitational presence has implications for the ultimate fate of the planets. The interplay between Jupiter's mass, the Sun's evolving luminosity, and the orbits of other planets influences how the solar system might change over billions of years. Some models suggest that Jupiter's gravity might help prevent Earth and other inner planets from spiraling inward or outward dramatically as the Sun ages, providing a more consistent environment that supports planetary stability until the Sun exhausts its fuel. Without Jupiter, the solar system's future could unfold less predictably. Greater orbital instabilities might lead to planetary collisions or ejections, fracturing the system's harmony. These possibilities underscore how Jupiter's massive scale contributes not only to past and present solar system dynamics, but also to its long-term evolution. Finally, considering the broader context of planetary systems beyond our own, comparisons with exoplanet discoveries highlight Jupiter's uniqueness and importance. Many discovered exoplanetary systems feature hot Jupiters, gas giants orbiting extremely close to their stars, often disrupting the formation of smaller terrestrial planets. Our Jupiter's position, relatively far from the Sun, helps preserve the inner solar system as a place where Earth-like planets can exist and flourish. Without a Jupiter-like planet in a similar position, it is questionable whether stable terrestrial planets could maintain conditions suitable for life. The study of exoplanet systems reinforces the conclusion that Jupiter's role is vital in maintaining a habitable zone within the solar system. In summary, Jupiter's gravitational influence extends across space and time, affecting the structure, dynamics, and habitability of the solar system. Its absence would set off a cascade of changes, altering planetary formation, asteroid and comet trajectories, impact rates, and even the potential for life itself. Jupiter is far more than a colossal ball of gas. It acts as a central actor in the continuing story of our cosmic home. Beyond the gravitational choreography and the roles Jupiter plays in shaping planetary behaviors, another key aspect to consider is how Jupiter's absence might alter the very composition and evolution of the solar system's small bodies, including comets, asteroids, and meteoroids. These objects carry crucial information about the history of the solar system, act as building blocks of planets, and, through impacts, have influenced Earth's environment and biology over billions of years. Jupiter acts as a powerful gravitational gatekeeper to the inner solar system, affecting the distribution and movement of countless minor bodies. Its immense gravity can both capture and redirect asteroids and comets, changing their trajectories in ways that influence the likelihood of their collision with Earth or other planets. Without Jupiter acting as a formidable shield, the inner planets could face a dramatically different impact history, one potentially far more violent or unpredictable. To delve deeper, it helps to consider the two major populations of small icy bodies influenced by Jupiter: the Jupiter family comets, JFCS, and the long-period comets, LPCS. Jupiter family comets originate from the Kuiper Belt, a vast region beyond Neptune filled with icy remnants from the solar system's formation. These comets occasionally wander towards the inner solar system under the combined gravitational influences of Neptune and Jupiter. Jupiter's gravity acts, in essence, like a shepherd, capturing many of these comets into shorter, more predictable orbits. This leads to a relatively stable and somewhat regulated influx of comets around the Sun and Earth. In a solar system without Jupiter, this regulation would be disrupted. The Kuiper Belt objects would still exist, but without Jupiter's gravitational influence funneling many of them inward or away, the frequency, timing, and orbits of comets entering the inner solar system would change. This could mean a higher rate of sudden, unpredictable comet visits, raising Earth's exposure to catastrophic impacts even as fewer comets might settle into stable, repeated orbits. This route of chaotic comet migration could result in a less stable environment for life on Earth. Long-period comets, coming from the hypothesized Oort cloud at the solar system's edge, are influenced by gravitational nudges not only from passing stars and galactic tides, but also by the giant planets, particularly Jupiter. Jupiter's gravity can redirect these comets, either ejecting them back into deep space or sending them into the inner solar system, where they might become visible and sometimes hazardous. Without Jupiter, the frequency of long-period comets reaching Earth could increase again, as there'd be less gravitational filtering. In turn, this could mean Earth faces an elevated risk of rare but devastating impacts that influence climate and biological evolution. Furthermore, when thinking about the asteroid belt, it's important to recognize how Jupiter's influence has prevented this band of rocky debris from coalescing into a planet. The gravitational disturbances, known as resonances, continually perturb the position and movement of asteroids, preventing their growth and maintaining the belt as a collection of countless smaller objects. Without Jupiter, the asteroid belt's dynamics might have permitted these materials to aggregate over millions of years, potentially forming another smaller terrestrial planet or a mini-planetary system between Mars and Jupiter. If such a new planet had formed, Earth's environment could be very different. The gravitational influence of this additional world might disrupt Earth's orbit or alter the delivery rate of volatile materials critical for life. Conversely, in the absence of Jupiter, a less disturbed belt with fewer large objects might reduce the number of asteroid impacts on Earth, shifting the timeline and nature of events that have driven biological and geological evolution. Scientists have used computational simulations to explore these possibilities, studying how the early solar system's small body populations would evolve without a massive gas giant. These simulations reinforce a picture of a more chaotic inner solar system, where impact rates on Earth and its neighbors could have been higher, lower, or highly variable, depending on the timing and nature of Jupiter's influence, or its absence, and the extent to which other planets filled the gravitational gap left behind. Impact events themselves are not just destructive forces, but also key agents of change shaping planetary surfaces and possibly life. Mass extinctions linked to impacts, like the one that ended the age of the dinosaurs roughly 65 million years ago, have profoundly reshaped Earth's biological trajectory. Some impacts brought potentially life-enabling compounds, such as amino acids or water, and may have jump-started life's chemistry on our planet. Without Jupiter, the frequency and size distribution of these impacts could have followed an entirely different pattern, possibly delaying or preventing the emergence of complex life. Switching gears to another arena influenced indirectly by Jupiter, the solar system's magnetic environment owes much to this giant planet. Jupiter's magnetic field is the largest and most powerful among the planets, extending millions of kilometers into space and influencing charged particles in the vicinity. This field interacts with the solar wind, a stream of charged particles emitted by the sun, forming a vast magnetosphere. In fact, Jupiter's magnetosphere is so strong that it creates intense radiation belts enveloping the planet, posing a significant challenge to spacecraft, but offering vital data about magnetic phenomena. The large-scale magnetic disturbances caused by Jupiter protect its moons and affect the behavior of energetic particles across the solar system. One fascinating consequence is how these interactions contribute to the auroras on Jupiter, which are different in nature from Earth's, but reveal much about planetary magnetic fields in general. Jupiter's strong magnetosphere also deflects some charged solar particles that might otherwise penetrate the inner solar system more efficiently. Without Jupiter, the overall distribution of energetic particles and solar wind interactions within the inner solar system could be altered. While Earth's magnetic field offers its own defense, the planet would likely experience different patterns of space weather effects, possibly influencing atmospheric chemistry and satellite behavior. On a more cosmic scale, the discovery and study of Jupiter-like exoplanets orbiting other stars have reshaped our understanding of planetary systems, and in turn, our comprehension of why our solar system developed as it did. Many of the gas giants found orbit very close to their stars, unlike Jupiter. These so-called hot Jupiters would not allow stable terrestrial planets to exist in the habitable zone, the region around a star where conditions could allow liquid water. That makes our Jupiter's relatively distant position doubly important. It stabilized the system and allowed Earth and its neighbors to thrive. The absence of Jupiter might mean not just more chaotic interplanetary orbits, but also a solar system architecture more like those observed around other stars, often dominated by close-in giants with little room for smaller, rocky planets in stable orbits. This suggests that Jupiter's presence is a key factor in the development of a solar system conducive to life as we understand it. Returning to our own solar system, it's important to recognize the role Jupiter's presence also plays in the story of planetary climates, especially Earth's. The gravitational influence of Jupiter can affect Earth's orbit and axial tilt over long timescales, contributing to cycles known as Milankovitch cycles, which influence Earth's climate patterns and thus the rise and fall of ice ages. These orbital variations modulate sunlight distribution and have played a role in shaping Earth's ecological and evolutionary history. Without Jupiter, Earth's orbital parameters might shift more unpredictably, leading to more extreme swings in climate or less stable environmental conditions over millions of years. Such instability could make it harder for complex life to develop and thrive, as ecological niches would be subject to greater volatility. Even Mars' current climate and surface characteristics may owe something to Jupiter's presence. Mars exhibits seasons and polar ice caps, but its thin atmosphere and lack of a global magnetic field make it vulnerable to solar wind stripping. Jupiter's gravitational position helps keep Mars' orbit relatively consistent, possibly contributing indirectly to its retention of seasonal ice and geological features. From the perspective of planetary science, the absence of Jupiter would also limit humanity's opportunity to study planetary atmospheres, magnetic fields, and giant planet formation. Missions like Juno and past missions like Galileo have provided windows into gas giant internal structures, atmospheric dynamics, and magnetospheres that cannot be duplicated in the inner solar system. Without Jupiter, such knowledge would be lacking, delaying or constraining our understanding of planetary science more broadly. In summary, the influence of Jupiter spans the entire solar system, extending from orbital mechanics and impact risks to planetary climates and space physics. Its massive presence acts as a sculptor of environments, an orchestrator of cosmic chaos, and a protector of terrestrial life through indirect means. Imagining a solar system without Jupiter reveals just how interconnected and delicate the balance is that allows planets like Earth to exist in stable, life-supporting conditions. This perspective underscores the importance of giant planets in planetary system architecture and highlights how the myriad factors that appear fixed in our sky are, in reality, the product of complex and finely tuned interactions that have unfolded over billions of years. Removing one such pivotal player as Jupiter cannot help but ripple outward, reshaping the entire system in ways both subtle and profound, altering not only the trajectories of worlds, but also the very potential for life to take hold and flourish. Another dimension to consider when pondering a solar system without Jupiter involves the formation and evolution of the other giant planets themselves: Saturn, Uranus, and Neptune. The presence of Jupiter early in the solar system's history played a critical role in shaping the architecture of these outer worlds, and its absence would likely have led to a very different configuration. Jupiter is thought to have formed relatively quickly, within the first few million years after the Sun's birth, by accreting vast amounts of gas and ice from the primordial solar nebula, a disk of gas and dust surrounding the young Sun. This rapid accumulation established Jupiter as the largest and most massive planet, its gravity influencing the growth and orbits of the other giants. The gas giants are not isolated. They interact gravitationally, migrating in the forming planetary disk and occasionally altering each other's paths. Without Jupiter's mass dominating the outer solar system early on, the other giants likely would have formed under different conditions. For example, Saturn, normally the second most massive gas giant, might have taken over the role of shepherding the remaining gas and icy planetesimals, possibly growing larger or migrating differently in response to the altered gravitational landscape. Similarly, the ice giants Uranus and Neptune, already the outermost planets, may have experienced changes in their orbital positions or sizes, or even failed to form in their familiar locations. This idea of planetary migration, where planets do not stay fixed in the orbits where they first form, is key to understanding planetary systems beyond our own. Models such as the Grand Tack hypothesis suggest that Jupiter itself might have migrated inward toward the Sun before reversing course, the tack, and moving outward to settle near its current orbit. This migration would have shaped the mass distribution and composition of the inner planets, including Earth, by stirring and scattering smaller bodies in the inner disk. Without Jupiter to instigate this migration, the inner solar system might contain a different arrangement of terrestrial planets, with consequences for their sizes, compositions, and positions. For instance, the asteroid belt structure might have been more continuous or more clumpy, changing the raw materials available for planet formation. The absence of Jupiter's inward then outward movement might mean Earth never received the particular mix of volatile compounds necessary to seed oceans and atmosphere, influencing its habitability. Moreover, Jupiter's role in stabilizing the solar system's orbital dynamics extends to the long-term gravitational interactions among the planets. Without this dominant mass, the solar system could experience higher levels of orbital chaos over hundreds of millions or billions of years. The orbits of the planets might become more eccentric or inclined, increasing the likelihood of close encounters or even collisions among planets or smaller bodies. While the current solar system appears relatively stable on astronomical timescales, that stability partly arises from Jupiter's presence as a gravitational anchor. Exploring the chemical composition of the solar system also highlights Jupiter's significance in delivering elements vital for life. By capturing and redirecting comets and asteroids rich in water and organic materials, Jupiter contributed to the distribution of these substances closer to the Sun. This delivery mechanism augmented the volatile inventory of Earth and the other inner planets. Without it, Earth's early environment might have been much drier and less hospitable. Scientists studying meteorites, the fragments of asteroids that reach Earth, recognize traces of interactions shaped by Jupiter's gravity. The distinction between carbonaceous chondrites, rich in water and organic compounds, and other meteorite types suggests the influence of planetary resonances and gravitational perturbations in sorting these materials. A solar system without Jupiter might have a markedly different pattern of meteorite fall, affecting the raw ingredients that helped give rise to life. Turning our gaze beyond our own neighborhood, the presence of a giant planet like Jupiter is important for understanding planet formation in a broader cosmic context. Studies of other star systems have found that giant planets often play decisive roles in shaping the composition and architecture of entire planetary systems. Some exoplanet systems contain super-Jupiters or multiple gas giants that influence the habitability potential of any smaller rocky worlds orbiting nearby. In these stellar neighborhoods, the presence or absence of a Jupiter-like world can alter the migration paths of both rocky and icy planets, change system stability, and affect the prevalence of orbit-crossing bodies. This adds a crucial layer to the search for life beyond Earth, emphasizing the importance of detecting giant planets alongside smaller terrestrial candidates. The dynamics of moons orbiting gas giants also illustrate another facet of Jupiter's significance. Jupiter's 79 known moons vary widely, from tiny captured asteroids to large, geologically active worlds. One of the most fascinating is Europa, an icy moon thought to harbor a subsurface ocean beneath its frozen surface, a potential habitat for life. The gravitational interaction between Jupiter and its moons generates tidal heating, keeping Europa's ocean liquid and driving geological activity. Without Jupiter's immense gravity, such tidal interactions would be absent or dramatically different, potentially depriving these moons of the energy needed to maintain subsurface oceans or geological renewal. This reduces the number of potentially habitable environments in the solar system and limits the variety of places scientists can study for answers about life's possibilities. Even moons like Ganymede, the largest moon in the solar system, have magnetic fields influenced by their interactions with Jupiter's magnetosphere. The complex interactions within this mini-magnetosphere system help drive particle acceleration and auroral activity, revealing much about how magnetic fields can play roles in planetary environments. Without Jupiter, these natural laboratories for studying planetary magnetism would not exist. Jupiter's influence also extends to shaping our cultural and scientific understanding of the solar system. Its brightness and size have made it a familiar object in human night skies across history, inspiring myths and driving early telescopic observations. From Galileo's pioneering studies revealing Jupiter's moons in the early 17th century to modern missions like Juno currently orbiting the planet, examining Jupiter has expanded our knowledge of atmospheric physics, planetary magnetism, and the solar system's origins. Without Jupiter, the trajectory of planetary science itself would have been quite different. Its unique properties and accessibility have made it a vital subject for spacecraft exploration, informing theories about giant planet formation, weather dynamics like jet streams and storm systems, radiation environments, and more. Scientists rely on this knowledge to make sense of more distant worlds and guide future missions. Considering Jupiter's prominent role in generating the solar system's gravitational waves and contributing measurable effects to the overall gravitational environment reveals yet another subtle consequence of its absence. While these waves are far too weak for us to feel directly, they contribute to the complex gravitational interplay that subtly guides the motions of all solar system objects. Removing such a massive planet would reduce this background gravitational complexity, potentially resulting in altered orbital resonances over vast timescales. Finally, reflecting on the interconnectedness of all these factors, the absence of Jupiter would have set off a cascade of changes rippling across billions of years. The solar system as a whole, a collection of planets, moons, asteroids, comets, magnetic fields, and radiation belts, is not merely a set of independent objects, but a finely intertwined system governed by gravitational and physical interactions. Removing Jupiter, the largest piece in this cosmic puzzle, would jeopardize the stability, configuration, and possibly even the very existence of terrestrial life as we know it. In summary, while it might seem at first glance that removing a single planet, even one as large as Jupiter, is a straightforward substitution, the reality is far more complex. Jupiter's role as a stabilizer, protector, and influencer stretches from the deepest reaches of the Oort cloud to the surface of Earth, affecting conditions that have shaped planetary orbits, climate cycles, impact history, and opportunities for life. Its absence would produce a solar system fundamentally different in architecture and habitability, perhaps less hospitable to the emergence of complex organisms. Understanding Jupiter's myriad contributions not only enriches our appreciation of our home planet's place in the cosmos, but also guides us in interpreting planetary systems elsewhere, deepening our grasp of what it takes to nurture life among the stars.